A line and a circle have only three ways to meet: miss completely, cut straight through, or just barely kiss it at a single point. That last one, the line that touches a circle at exactly one point, is a tangent, and it hides one of the cleanest right angles in all of geometry. In this video, we'll nail what a tangent is, the one theorem everything rests on, and how many tangents you can draw from any point. Let's go. Picture a straight line drifting toward a circle. Far away it misses entirely, no common point. That's a non-intersecting line. Push it closer and it slices through at 2 points. That's a secant. Push it until it only grazes the edge at one single point. That's a tangent. 0 points, 2 points, 1 point, non-intersecting, secant, tangent. Here's the elegant bit. A tangent is really the limiting case of a secant. As the 2 points where a secant cuts the circle slide toward each other, the little chord between them shrinks until both points merge into one. At that instant, the secant has become a tangent, and the single point where it touches is called the point of contact. Now the theorem the whole chapter leans on. Theorem 10.1. The tangent at any point of a circle is perpendicular to the radius drawn to the point of contact. Why is it exactly 90 degrees? Because of all the distances from the center to the tangent line, the radius to the point of contact is the shortest, and the shortest distance from a point to a line is always the perpendicular. So radius meets tangent at a perfect right angle. Three things follow immediately. At any single point on a circle, there's exactly one tangent. A whole circle has infinitely many tangents, one at every point, and at most 2 of them can be parallel to a given line. Those 2 touch at the opposite ends of a diameter. Best of all, that right angle hands you a right triangle. If a tangent touches at P and the center is O, triangle OP anything on the tangent is right-angled at P, so Pythagoras is always available. Let's use it. A tangent touches a circle of radius 5 at P, and a line from the center O meets the tangent at Q with OQ equal to 12. Find PQ. Since the radius OP is perpendicular to the tangent, triangle OPQ is right-angled at P. So PQ is the square root of OQ squared minus OP squared. That's the square root of 144 minus 25, which is the square root of 119. Done with one right angle. So a tangent touches at one point and stands perpendicular to the radius. Next question. From a given point, how many tangents can you even draw? The answer depends entirely on where that point sits. 3 cases. From a point inside the circle, 0 tangents. Every line through an inside point has to cut the circle in 2 places, so it's always a secant, never a tangent. From a point exactly on the circle, 1 tangent. And from a point outside the circle, exactly 2 tangents. 0, 1, 2, inside, on, outside. Those 2 tangents from an outside point have a beautiful property. Theorem 10.2. They're equal in length. Here's the quick proof. Call the external point P and the contact points Q and R. In triangles OQP and ORP, OQ equals OR because both are radii, OP is shared, and each has a right angle at the point of contact. That's the RHS congruence condition, right angle, hypotenuse, side, so the triangles are congruent, which forces PQ to equal PR. The 2 tangent lengths are equal. 2 bonus facts drop out of that same pair of congruent triangles. First, the line from the external point to the center, OP, bisects the angle between the 2 tangents. The center always sits on that angle bisector. Second, the angle between the 2 tangents and the angle they subtend at the center add up to 180 degrees. They're supplementary. That second fact alone solves a lot of exam questions. To find a tangent length directly, use the right triangle again. Length equals the square root of OP squared minus R squared, where OP is the point's distance from the center and R is the radius. Flip it around in this classic. The tangent length is 24 and OQ is 25. So the radius is the square root of 25 squared minus 24 squared, the square root of 625 minus 576, the square root of 49, which is 7. One application examiners love: when a quadrilateral is drawn around a circle so all 4 sides are tangents, The sums of opposite sides are equal. AB plus CD equals AD plus BC. It falls straight out of equal tangent lengths from each corner. A neat corollary. Any parallelogram that wraps around a circle must actually be a rhombus. A quick angle example. Two tangents, TP and TQ, are drawn from an external point T, and the angle at the center, POQ, is 110 degrees. Find the angle between the tangents, PTQ. They're supplementary, so PTQ is 180 minus 110, which is 70 degrees. One subtraction. Your turn. The question's on screen. Pause if you like, but try it first. 10 seconds, go. The tangent is perpendicular to the radius, so the radius is the square root of OQ squared minus the tangent length squared. The square root of 25 squared minus 24 squared, which is the square root of 49 equal to 7 centimeters. That's option A. Lock it in. A tangent touches at one point and is perpendicular to the radius there. From a point, 0 tangents inside, 1 on, 2 outside, and the 2 from outside are equal in length, with the center angle and the tangent angle adding to 180. Last challenge. It's on the screen. Don't say it aloud. Type your answer in the comments and I'll pin the right one. And that's circles. Tangents, the right angle theorem, and equal tangent lengths, all from one radius meeting one line. Free notes with 60 practice questions are in the description. Subscribe for the next chapter. This is Clarix. Keep going.